So we have a teeny tiny bit left. 12.5 is relatively short. It's mostly going to help you identify types of data. So we've spent all this time creating histograms. We've talked about averages. You're going to have to create a bunch of histograms. What we're going to do here is talk about the normal curve, but really we're going to talk about a bunch of different data sets. So ultimately, if your type of information, when you create a histogram for it, if it has a certain shape to it, it has a certain type of distribution associated. So you can create histograms, that are kind of all over the place. So you don't really know anything that's going on. That doesn't happen as often. If you think of like most things, there's going to be some type of shape associated purely based off the topic that you're choosing. So I just need to pull up my PDF real quick because I'm behind this morning. Come on, computer. Right here, here we go. Okay. So when we look at a histogram of a data set, the shape can tell us a lot of information. Okay. So we're just going to take a look at a few common shapes, but there's more of them. So we're going to take a look at a few common shapes. And then for each of these, I'm going to give you an example of data that would probably have that particular shape. So the first one is called our rectangular distribution. And the name on this sounds exactly like the shape it makes. It's a rectangle. So when you go ahead and create that histogram, you've got your values down here. You've got your frequency going up here, and you've got all of those midpoints of your classes down here. For a rectangular distribution, you're going to have a very rectangular shape. So let's see if I can draw this decently. There we go. So pretty much all the values are the same across the board. Everything appears at the same frequency or close to it. It's not necessarily going to be perfect. Okay. So it might be that some is a little bit higher than others, but it has overall a rectangular shape. So in a rectangular distribution, all the observed values occur at the same frequency. Off the top of your head, do you have any ideas of like something realistic that if you were to plot its data, maybe it has a rectangular shape? So everything happens evenly. It's totally okay if you can't think of one.
No, I can't.
That's okay. Figure I asked, why not? So one good example would be maybe if you roll a die and you roll a die like 1,000 times, you have the same chance of getting every single side. It's probably going to happen pretty evenly across the board. Or like flipping a coin, heads and tails. Going to happen probably an equal number of times. You might have 10 heads in a row, but then you're going to counterbalance it where you might have a lot of tails in a row. So for example, if a die is rolled many times, we would expect each number to occur at the same frequency. So that histogram would probably be rectangular. Same thing if you were to shuffle a bunch of cards together, pull one out, and you do that hundreds and hundreds and hundreds of times, it's probably going to have a rectangular shape because you're probably going to pull each card an equal number of times. Does that make sense?
Yes.
Okay. The next type of distribution we have, oh, why is it moving? It's called a J-shaped distribution. I'll do my best to make this look as close to a J as I possibly can, but it's gonna be hard. So we've got the values, we've got our frequency up here, and I'm gonna do 2 of these. I'm gonna go ahead and copy this. Because ultimately your J can go either way. But it looks like a J because it's basically going to be constantly rising like a J does. It might plateau a little bit, but that shape is always going to be getting higher and higher and higher. So if you were to kind of smooth out this, you would have a J sitting on top. Okay. Or it can go the reverse direction. So it could start with a really high frequency and then keep getting lower and lower and lower and lower. And so you have a curve in this direction. So in J-shaped distributions, the frequency is constantly increasing or decreasing. So it's either always climbing up or always falling down. In terms of real life examples, this is really hard to kind of come by. The best example I can possibly give you is if you think of the number of hours people study per week, probably has a shape like this. A lot of people studying a low amount, a lot of people studying like, you know, say this is like 1 hour a week, 2 hours a week, 3 hours, 4 hours, 5 hours, 6 hours. People that are studying 20 hours are far and few in between. So it likely has this shape of constantly going down. So for example, the number of hours studied per week may have a distribution like this. But again, not as frequently. Okay. Good so far on these shapes?
Yes.
I think you'll really like the homework for this section. It's identifying from the picture what type it is, and then also if you have a scenario, which situation does it fall under? And there's going to be a few scenarios to pick from. So this homework should take you probably like 20 minutes. The third shape is bimodal. And so we learned about modal classes. What does bimodal mean? What do you think of with bi? Usually there's a single modal class. So if it's bimodal, how many are there?
Double?
Yeah, it's going to be double. So there's going to be two of them.
Okay.
So ultimately, what you're going to see for a bimodal distribution is two of these bars are going to shoot way up above the rest of everything else. So you've got some information here, some information here, and then you've got one bar that's gigantic. Some more stuff, more stuff, more stuff, more stuff, another. And they don't necessarily have to be the same amount. So there's clearly one that's higher than the other, but there's still two that sit way above everything else. So for a bimodal distribution, is one that has two non-adjacent values occurring more frequently than any other values. Okay. So if they were right next to each other, that's not quite bimodal. Like if I had really this not here, and instead I had this bar being super high, if I just changed my classes slightly, those would get lumped together. So that's why it has to kind of be separated from each other. Okay. Any thoughts maybe on a type that would be bimodal? So two things appear more frequently when you have two distinct divisions of individuals.
Like in a group?
Mm-hmm.
I'm not really sure. Like maybe a mm,
Think of maybe something that has two averages. If I split a group of people into two categories, they'll each have their own kind of unique average or unique mode. Then when I combine
mhm.
them, I still have two different modes because those two groups of people were different.
Like if a group averaged a C in a test and the other group averaged an A, like that.
Yeah, you could do something like that. Absolutely. So if you kind of broke it up maybe into honors students versus non-honor students, you've got
Mhm.
an or GPA that appears more frequently because you guys tend to have higher GPA. And then if you do non-honors, you're going to have a different mode because they have a different average. So yeah, absolutely. And then another example that also happens, and you might see this in some of your projects, if you have like men and women as well, um, they have kind of their own average height. So like there's a height for women that appears more frequently because we tend to be shorter on average, whereas men tend to be taller. So their average height is going to appear at a different value. So you see those kind of points up. So one bar being for the women's mode, a different bar being for the men's mode. So something you can make some type of distinction between groups, that's when it typically happens. So I'll give you just that short example. If we measured heights of men and women, there would likely be two higher frequencies. One for the men's height and one for women's. Okay. Those don't need to be possessive. Like most men, you're probably going to see a lot of people at like 5'8". That's going to be a height that most men are. So that bar will kind of pop up. For women, it's probably something like 5'4", 5'5". So you'll see those two values pop up on the chart. Okay. All right. So we really have two more distributions left, and these are the only ones we're going to talk about. The fourth one is what's called skewed. And I won't lie, this one is counterintuitive to what the graph actually looks like. So when the first time I saw this, I completely mixed them up. So I'm not going to bother putting values and frequency on it. So you have skewed. Maybe I have a histogram that looks like this. Everything's kind of grouped together here. Falls down, falls down. And then I have basically this long tail at the end here. Okay. Then I could reverse it. I could have a lot of information on this side. It's so hard to draw these nicely. And then I have kind of a long tail over here. Okay. So they're skewed to one direction. Which direction would you want to say this is skewed, the left or right?
To the left?
That's what I would think too, but it's not.
Mm-hmm.
So this is the one that's skewed to the right.
Okay.
So I've made that same mistake before. So this one is skewed to the right. And this one is skewed to the left. If my pen wants to write, I think there's like a dead pixel in this area. Nope, still not writing. There we go. This one is skewed to the left. Okay. Mostly it's going to be which side that tail is on. So the long tail is on the right, the long tail is on the left. That tells you the direction of it. But I think because all the data is sitting on the left, it's skewed to the left, but I was wrong too. So a skewed distribution has what we call a tail at one end. The side the tail is on is the direction of the skewed distribution. Okay. So most data is in one area, but then you have a few people that have values that are far off at one end. Any demographics that you could think of that maybe could cause something like this, or some type of thing you would notice few people having a larger quantity than the other?
Income?
Income, yeah. Most people sit here. Then you got that fancy 1% that has so much money that they're all the way at the other end of the spectrum. So income is definitely skewed to the right. Okay. So for example, annual income would be skewed to the right. Since few families would make a large amount of money. Okay. Another one is also number of kids. Most people have between 0 and 4 kids. But then you've got the Duggars with what, like 19 of them. A couple of my friends, they're one of like 10. You've got people that have large amounts of kids, which great. can't imagine it, but, but absolutely it can happen. So that's another example of something that's skewed to the right.
Yeah.
All right. The one nice thing that happens as a result of these skewed distributions is there's kind of a nice order to that mean, median, and mode. You could add up all of these data values, find your average that way, but really it will follow a nice pattern. Okay.
Okay.
So I'll show you for each of them. If you just kind of smooth it out, it has a shape like this. And for skewed to the left, it has a shape like this. Here's left, here's right. The mode is the one that's always the most straightforward because it's the tallest point on the graph. This number would be the one that appeared the most. This is what appears the most. So this is our mode. Okay. Then what falls closer to the tail is going to be our mean. And then last but not least, our median is going to fall in between these two. Let's see if I can fit this in somehow. So the median will fall in between. So this happens majority of the time. Not always, but most of the time it will. Okay. All right. So our very last type of distribution is where we get the name of this section. It's the normal distribution. And when you hear the word normal, what do you think of?
Like the most common.
Yeah. So this is going to be our most common piece of information. If you take into account like ages of individuals, if you take into account like anything that has to do with like your body, like heartbeats per minute, blood pressure, stuff like that. If you collect all that type of data, it's probably going to be a normal distribution because people are normal in that sense.
Yeah.
So ultimately, the shape of this is what's known as a bell curve. But you've got one number right in the middle. That's going to be our mean, and it's going to be our median, and it's going to be our mode. And then it's symmetric around that. So it does the same thing on both sides. And it's going to ultimately taper off into some tails. Right? So this value right in the middle is going to be the mean, the median, and the mode, which is fantastic. All the measures of average are exactly the same, and that is our best case scenario we can possibly have. Okay? So the normal, or you might hear it as Gaussian, which is named after a mathematician, distribution, is a symmetric distribution. Further, we have a bunch of different stuff. Okay. The graph is called a normal curve. The curve is bell shape. And symmetric about the mean. And the mean, median, and mode all have the same value and occur at the center. Okay. So if you kind of draw over the shape, it's got like a bell to it. Okay. The other really great thing that happens from our normal distribution is because of the symmetry, a lot of data is going to fall real close around the mean. So we don't talk about standard deviations in this class, which is kind of a measure of like variety and how far out things go. But it's basically going to give us, starting from that center point, a distance we have to travel in each direction. Okay. So I'm going to draw our bell curve down here. And then smack dab at the middle is going to be our mean. If it wants to go straight, there we go. So here's our mean in the middle. And then it's going to do the same thing on both sides, and it tapers out. Oh, no, don't. If I can make this look symmetric, that'll be good. Close enough. Okay. So I'm going to put a little thing up here. You can put it underneath, though. A standard deviation is a measure of, you can think of it as variety in the data. Okay. So from that center point of mean, if I go out one standard deviation in each direction, then here in the middle, would be 68% of our data. Okay. So this is one standard deviation in each direction. We will never make you actually calculate these. You're not going to be asked to find that stuff. You just want to remember how much data lies within there. But in total, from here to here, 68% of your data will lie within it. If you go out another standard deviation, so it's going to be the same distance, then within the distance between these two standard deviations, the majority of your data will lie here. So in between these two values, 95% of your data will be within there. And if you go out one more, most of your data will be within 3 standard deviations. So we go out one more of whatever this quantity is. And between these two values, 99.7% of our data will be here. Okay. So I'll summarize all of this, don't worry. But just kind of picturally, within 3 standard deviations, most of your information is going to be there. There's not much off at the ends, 0.3% outside of this range. So in any normal distribution, approximately 68% of the data lies within one standard deviation of the mean. So within those range of values, 68% of your information should be there. Approximately 95% of the data lies within two standard deviations of the mean. And then finally, approximately 99.7% of the data lies within three standard deviations of the mean. Okay. So predominantly, you just want to remember those percentages from here. I'm going to show you just an application of it, and then we'll ask just a simple question. Okay. But does this make sense so far? Do you have any questions at all?
Do you need to know how to figure out what the standard deviation is? Oh, okay. Okay.
If you take a statistics class, yes, you'll figure out how to do that. But no, we're not going to make you. If you want to look it up for your project, feel free, but I would not make you at all.
Mm-hmm. Okay.
That's not part of our curriculum.
Okay. So I'm good.
So let's just look at one example. Annual daycare cost per child is normally distributed with a mean of 8,000 and a standard deviation of 1,500. We want to figure out, oh, sorry. We want to figure out what percent of the data pays an annual daycare fee between $5,000 and $11,000. Okay. So we're going to have to figure out which of these scenarios we're in. Are we in 1, 2, or 3 standard deviations? So what I'd recommend doing is draw yourself a little picture and put 8,000 right in the middle. If you go 1 standard deviation in each direction, what would these amounts be?
Like subtracting 1,500 from 8,000 and then adding.
You got it. So this one would be 6,500 and this one would be 9,500. So the distance or that difference is 1,500. And then you just keep doing this. You can go out a total of 3 if you want. Go out another standard deviation for 1,500 in each direction. And that puts you at 2 standard deviations each direction. So what would those values be?
5,000 and then 10,500 or 11,000.
11,000. Good. And that's exactly the range we're looking in between. So that range is 2 standard deviations off that mean. How much of the data is going to be within these values?
Is it the same 95%?
95% of people will pay between 5,000 and 11,000 for their childcare. You got it.
Okay.
If you go one more because you want to see those third standard deviations, you can, but we don't need to for this question. But this would be 12,500. This would be 3,500. And this would be 3 in each direction. So 99.7% of people would pay between 3,500 and 12,500. So the range, 5,000 to 11,000, is 2 standard deviations from the mean of 8,000. So 95% of the data would fall in this range. Okay.
Do the percentages stay the same for every example or
Everyone.
question?
Mhm.
Okay.
Yeah. The difference is it'll just have a different mean and a different standard deviation. So if you're working with annual income, the mean is probably going to be something like, I don't know, like 75,000 maybe. I don't know what it is. And then your standard is probably going to be a lot more, like 15,000 instead. So those will be scaled to your data. That is it for this section.
I was sorry.
Yes. So usually when it's not honors, this is our last sections we go through, which is nice before your final, just because it is short. But this stuff is most applicable to stuff you can do. So I'm just twisting all the stuff around to be able to let you guys work on like something enjoyable for your project.
Yeah.
All right.
I have a question for the 4th graph you did. How did you how did I get the median and the mode, but how did you do the
mean? Yeah. So it's because you have a large quantity this way, pulling that average towards it. So your annual income, or if you looked at the notes from the last section, you had all the salaries of those employees. When you put the one salary that's all the way on the opposite spectrum, it made your mean a lot higher. So that distribution of those incomes or those salaries followed this. Most of the employees fell within the 50,000 mark. And then you had that one guy making 944,000 or whatever it was. So it made your mean higher than it should have been. So it got sucked towards that tail end.
Okay. So the tail is higher than the other side.
Yeah. Because think like this could be like 0 here, and this could be 100,000 over here. And maybe your mean is like, I don't know, 60,000. Yeah. If you were to ignore this completely, your mean probably falls more towards the middle here. But by adding in these large quantities at this end, it's pulling that mean closer to the tail.
Okay.
And then same thing over here, most of your data is on this side, but you've got a few small numbers that are pulling it this way and biasing that mean. So like if I go, I'm gonna go back to this guy's stuff. Okay, so like here, we've got all of this information. Most people are sitting around 50,000, right? So you would expect the mean to be around 50,000 because most people are there. But because you have this one guy that makes our histogram have a tail end all the way in the 900,000s, your mean was 149,000. When you get
Okay.
rid of that tail and just work with the other people, your average is only 50,000.
Okay.
That
Makes
big
sense.
quantity drastically changes that mean.
Okay.